Alright, let's take a look at resistance and resistivity. So to start off, let's do a little bit of review. What is voltage? Voltage is electric potential. So it's kind of like gravitational potential energy, right? So if we have a wire, and on one end we have 10 volts potential, and then we have 0 volts potential, we also know that the electric field is defined as dV dx, at least for one dimension. So that means however much distance there is here, there's going to be a constant electric field pointing this way, trying to move charges along this wire. So that's what's trying to make our charges move in this wire, our electrons or our protons, or not protons, but positive charges, whatever you want to call them. But there's also stuff in the way. You can think of maybe atoms, because this wire is made up of atoms. There's stuff in here. There's a little bit of stuff. And we have our charge. I'm just going to use positive charge since it works out more nicely with the field and voltage and whatnot. But it works the same way for electric charge. It'll just try and move the other way. So we have this voltage trying to pull this electric charge through. You can imagine like there's just a big negative charge over here and a big positive charge here at the top. So they're both trying to push this charge down. Well, there's atoms in the way, so it's going to be bouncing around like a ball falling through a bunch of pegs, right? And that is going to cause resistance. You can think of it this way. The more pegs there are, the slower those charges are going to move. Um, and the same thing with the voltage. The more voltage, the faster those charges are going to move. So the number of pegs, effectively, is resistivity, denoted by Greek letter rho. So what else affects the resistance of a wire? What else affects how many charges can move how quickly through a tube like this wire? Well, if there's more area, that will increase the number of electrons that can flow, so it's reducing the resistance. And if the tube is longer, if the wire is longer, that will increase the resistance. So another way to think about this, it's kind of analogous to flowing water, like trying to suck water through a straw. You can go out and try this. So if you take a single straw and try and drink out of it, see how hard it is to suck up the drink. Then take two straws, two identical straws, and stick them end to end. So now you have a single straw that's twice as long. Try and use that, and you'll notice it's twice as hard. And if you take two straws and put them next to each other, so you're doubling the area now, it's twice as easy. So that's where we get our formula for resistance, rho times L over A, where A is the cross-sectional area of the wire. So if you imagine we just took a knife, cut this wire open, what is this cross-sectional area here? So there's your formula for resistance. And that, well, okay, so if we look at the same concepts we talked about earlier, with the voltage trying to pull the charges through all these pegs, we get Ohm's law, which just says that current, says that is a flow of charges, is equal to the voltage divided by the resistance. Now, what you need to remember here is that this only applies to a single resistor. This is only for when you have a uniform resistivity throughout your entire wire, your entire resistor, and you only have one wire as well. So in a circuit, for example, if we have this nonsense, like this, you can't just apply Ohm's law directly, because there's two resistors here. What Ohm's law will tell you is what is the voltage between these 2 points. Let's say this is a 2 ohm resistor, and we know there's 5 volts on this battery. Then this is all one continuous length of wire. There's no components breaking it up, so there's also 5 volts here, and 0 volts down here, if you want to say it that way. So now we know the voltage across this resistor, so we can use Ohm's law, I equals V over R, 5 over 2 amps. So we can use Ohm's law, and that will tell us the current through this single resistor resulting from the voltage across this single resistor. But that's all it tells us. We can never use Ohm's law for anything else, right? This is only describing what happens to a single resistor. So you should associate this equation with just a resistor. Like whenever you try to use this equation, you need to be looking at a picture like this. You need to ignore everything else outside. Just what is the voltage difference between these 2 points, and then what is the current through this single resistor. And that depends on the resistivity of just this resistor. All right. Okay. So hopefully that gives you a good understanding of the basics of resistors. Now let's look at resistors in parallel and series. So when we have a resistor in a circuit, we capture all of its characteristics using just its resistance. We don't care about its area anymore. We don't care about the length of it anymore. All of its properties are captured by its resistance, at least for ohmic resistors, which we kind of assume for any resistor you actually see in a circuit. So cool. We have, let's say 12 volts here. We have a neat little circuit with 2 resistors in parallel. Well, how do we combine these? Well, we don't know what the area or length of these are, but we know all their properties are captured by their resistance. So in other words, we can make up any area or any length or any resistivity we want, and as long as they math out to 4 and 8, it's fine. So let's just say for a second that these have the exact same length and the exact same resistivity. This one just has twice the area of this one, the cross-sectional area. Well, then if we put them together, that's equivalent to a single new resistor with the same resistivity and the same length, but 3 times the area. Oops, that's not the right formula. There it goes on the bottom. Same length, same resistivity, but 3 times the area. So if rho L over A was equal to 4, or, yeah. Am I thinking about this right? No. Okay. We'll try this again. So now let's look at resistors in parallel and in series. So we'll start with parallel. When we look at resistors in a circuit, we capture all of its properties just by looking at its resistance. We don't care about its resistivity or its area or its length anymore. We only care about all of them combined in the resistivity. That captures all of its properties as long as the resistor is ohmic, which we kind of assume for all the circuits you're going to be looking at in AP Physics. So what that means is when we try and combine 2 resistors in parallel, we can set any resistivity, any area, any length we want as long as they math out to 4 and 8. So what I'm going to do is I'm going to define those numbers conveniently. So I'm going to say, let's say this 8 ohm resistor is actually a resistor with resistivity rho, with length L, and with area A. And then for the 4 ohm resistor, I'm going to say I want the length to be the same, and I want the resistivity to be the same. So we'll set rho and L already. But now we need the resistance to be half. To be half. So with the only thing left to change being A, we'll set that to be 2A. So now, when we combine these 2 resistors, what we're effectively doing is we're just adding up their area, right? Because right now what we have is a little resistor like this, with resistivity rho and length L and area A. And then we have a bigger resistor like this, same length, same material. I'm just going to stick them side to side. So now we have a resistor with same resistivity, same length, but 3 times the area. So if this was equal to 4, and this was equal to 8, then this is going to be, let's see, we can just do 8 over 3. Right. And there's your final resistance of, or the effective resistance of combining these two. In other words, now we can redraw our circuit to look like this. Ohms. Yes. So this is kind of an intuition for why resistors in parallel will reduce resistance, which is why you get the formula 1 over R equivalent is equal to 1 over R1 plus 1 over R2. That way, your final resistance will always be lower than the two combined. And also, if you look at it this way, it's kind of like saying 1 over is, when you take 1 over of your resistance, you're just putting that area on top. And it's saying you're just adding the areas up, and then you're going to flip it back over to get resistance again. Alright, so that's resistors in parallel. Now let's look at resistors in series. So let's use the same numbers. Alright, so we have 12 volts, 8 ohm resistor, 4 ohm resistor. So I'm going to do the same thing to kind of build an intuition. I'm going to define these conveniently. Let's say this is resistance rho, area A, and now I'm going to say this has area 2, or not area, length 2L. This one is just rho L over A. So now when we combine these, we're taking a resistor like this, and then a resistor like this, that's twice as long. I'm just going to stick them end to end. Just going to stick them end to end. So our result is going to be a resistor with resistivity rho, area A, and length 3L. So we can see if rho LA was 4 ohms, then this is going to work out to 12 ohms. So that's why we get an effective 12 ohm resistor. So we can redraw this circuit like so. 12 ohms. 12 volts. So, and you can see why that is now, because if we're effectively adding the length, which makes sense if we're sticking them end to end, then we're just adding the numerators. So we can just add them directly. So that's why you get the formula R equivalent is equal to R1 plus R2 for resistors in series. So now in both of these circuits, once we've combined the resistors, so there's just one voltage source and one resistor, now we can use Ohm's law to figure out how much current actually flows through the circuit. Because if there's, so I do what's called the finger trick. So basically that's where you just pick 2 points where you know the voltage, right? Pretend these are on the wire. I just don't want to draw on the wire. So there's 12 volts difference between these 2 points on either end of the battery. I'm going to slide my finger along the circuit, and as long as I don't cross any components, as long as I'm just moving along open wire, the voltage will not change. So I can slide that finger over there, I can slide that finger over there, and so now you can see there's clearly 12 volts across this resistor. And then, so if we just now just zoom in on this part, we ignore everything in the outside world, now we can say Ohm's law, I equals V over R, with 12 volts, 12 ohms, so we're going to get 1 amp of current. And that's the current flowing throughout this entire circuit. Because this is kind of another finger rule. As long as you don't cross a junction, that is, your circuit hasn't split or joined, the current will remain the same. So here there's no splits or joins anywhere, so the current's always the same. Let's look at this other circuit we drew. So we do the same 2-finger trick, so this is still 12 volts. So we have 1 finger here, 1 finger here, so we go around, that's still 12 volts, that's still 12 volts. So then we do Ohm's law, I equals V over R, it's equal to 12 over 8 over 3, which is going to be, let's see, 36 over 8, which is going to be 9 over 2, hopefully. I think I did that math right. And there's our current. And so same thing here, there's no splits. But now, if we go back to our original circuit, now we know there has to be, what was the number? 9 over 2 amps. So what is that? 4.5 amps. There has to be 4.5 amps flowing out of this battery, and into the battery, really just through the battery. And there has to be 9.2 amps, or sorry, 4.5 amps flowing all along here, because there's no splits. But once we get to here, we don't know yet. We don't know anymore. We know there has to be a total of 4.5 amps flowing through this effective resistor, through both of these combined. But we don't know what happens in each one individually. However, here's what happens at every junction. The current going in has to equal to the current coming out. Let's call this I1, I2. This is saying I1 and I2 have to add up to I1, or sorry, I. And using that and the Ohm's law for each of these individual resistors, you can solve a system of equations to find the individual currents. Or, if you watch my next video, we'll take a look at how to use Kirchhoff's law to kind of solve a circuit more fluidly.